In this training module, we'll concentrate on the theory behind the FD322's operation, starting with the functional block diagram of the APU. The internal hardware and processes are shown inside the gray rectangle in this illustration. The process starts out with light from a laser diode being injected into the sensing cable, which is deployed on the fence. The light propagates through the sensing fiber and returns to the unit's detector, which converts the light into an electrical signal that is amplified and filtered. That signal is then fed into the digital signal processor, or DSP, where it's digitized and then split into two parallel processing algorithms. One of these is dedicated to detecting climb intrusions, referred to as P1 or processor 1, and the other to cut intrusions, referred to as P2 or processor 2. The outputs of these two processes are integrated by a logical OR function such that an alarm output can be generated by either a cut intrusion or a climb intrusion. The alarm and fault relays then present the results to the outside world. The DSP also controls the two communications ports, being TCP/IP and RS-232. The TCP/IP port supports remote alarm and fault monitoring and remote APU parameter setting, while the RS-232 port serves the purposes of parameter setting, APU status monitoring, and alarm data file handling. It does not, however, support alarm status reporting for system monitoring purposes. Now, let's briefly touch on the optical theory of operation, starting with the optical fiber itself. Our sensing fiber is 50/125 micron multimode type fiber that has been rigorously qualified as a sensing element. It's constructed from two layers of specially formulated glass, the core and cladding, and the primary difference between the two is their index of refraction. This difference creates a condition of total internal reflection, which allows the fiber to guide the light through it by a series of reflections, as though the fiber were a mirrored tube. The FD322 operates on the principle of polarimetric detection. Laser diodes naturally emit polarized light, and that light is launched into the sensing fiber. When the fiber is undisturbed, that is, not subject to external vibration, the laser light's polarization remains constant as it travels through the fiber. However, when the fiber is disturbed due to fence vibrations, the laser light's polarization changes in response to the magnitude and duration of the disturbance. The APU's receiver senses the change in polarization and produces a time-varying electrical signal that is processed by the DSP in order to sense events and alarms. Now let's move on to discuss the algorithms that the DSP uses to analyze the fence vibration signal. The algorithms can be broken down into three categories: wind processing, event processing, and alarm processing. They are under user control via a number of parameters that are adjusted by using the tuning software's parameter editor. An example parameter table can be seen on the right of this slide. We'll now discuss each of the processing algorithms and associated parameters separately and in detail. The wind processing algorithm has two controls associated with it. First, it can be enabled or disabled, although it's highly recommended that it be enabled for all applications. There is one variable associated with this algorithm, and that would be the wind rejection parameter. This parameter allows the user to control the amount of dampening applied to the signal in the presence of a detected wind load. Wind processing works by continuously analyzing the fence signal for a condition known as wind load. This signal is representative of a more or less continuous fence vibration, which the DSP recognizes as wind. As a matter of fact, any continuous fence vibration will be recognized as wind, so keep this in mind if there are any nuisance alarm sources that might make the fence vibrate. Wind processing will work with these as well. Anyhow, the DSP dynamically adjusts the signal gain based on the detected wind load in an amount set by the wind rejection parameter value. This parameter is used to dynamically dampen the signal in the presence of wind load. Its value ranges from 20 to 80, and as a rule of thumb, its nominal value of 50 will compensate for winds up to 20 miles per hour. If you experience excessive wind-generated alarms, raise the wind rejection parameter by 10 or so and resume testing. Continue monitoring the zone for wind nuisance alarms and iteratively adjust the value up and down until the system performs to your satisfaction. This graph illustrates the operation of the wind rejection parameter. The wind load, shown on the horizontal axis, increases with wind speed, but is not a measure of wind speed in miles per hour. Rather, it is simply a number that assigns the maximum gain reduction to be applied to the signal. In this example, with the wind rejection parameter set to 60, the maximum gain reduction is about 10 dB, and the compensation levels off for all wind loads above 60. As previously mentioned, the default value of 50 is appropriate for wind speeds up to about 20 miles per hour. Increase the wind rejection if wind-related nuisance alarms occur, and monitor the system for performance. It may take several iterations to properly set this parameter. The next class of algorithms is called event processing. The DSP continuously analyzes the fence signal to qualify it in order to separate nuisance-generated disturbances from valid intrusion attempts. A probable intrusion-caused disturbance is called an event. Both climb and cut processors have controls and parameters associated with the event processing. First of all, either processor can be enabled or disabled. Next, each processor has adjustable sensitivity. Sensitivity is a gain adjustment that makes the sensor more or less likely to create events in response to sensor signals. Increasing the sensitivity makes the APU more responsive to signals, thereby creating events from smaller signals. Both climb and cut processors have independently adjustable sensitivity parameters. The next adjustable parameter is called low-frequency cutoff, and as can be seen in the parameter table, climbs and cuts have independent adjustments of this type. This parameter allows the setting of the lowest frequency that's analyzed by the APU in the event qualification process. Again, it's independently adjustable for both climbs and cuts. The graph shown here is an example of the tuning software's real-time mode. It gives a frequency domain representation of the fence signal as it occurs. The graph horizontal axis shows frequencies between 10 and 600 Hz from left to right, while the vertical axis shows the relative amplitude of the signal at those frequencies. The low-frequency cutoff, shown as a vertical red line here, is adjustable to any point in the frequency range. Only signals above the cutoff are processed by the DSP in the event qualification process. As will be shown in later examples in this training program, many nuisance alarm sources, such as wind, traffic vibrations, and power line-related vibrations, have strong low-frequency components. These can often be rejected by capturing such a signal using the real-time mode, analyzing it, and setting the low-frequency cutoff appropriately to reduce or eliminate the nuisance signal frequencies. The third and final sensing algorithm type is alarm processing. In this phase of sensor operation, the DSP analyzes recent events to determine whether or not an intrusion has occurred. Remember that an event is defined as a probable intrusion-caused sensor signal. There are 3 user adjustments related to alarm processing: event count, alarm relay time, and tamper enable. However, only one of them, event count, is actively involved with the actual determination of whether or not an intrusion has occurred. Note that both climb and cut processors have independently adjustable event counts. The event count parameter allows the user to choose how many events must occur in order to create an alarm. The set number of events must occur in a strict sequence that's defined by a set of alarm timing rules. Let's start by analyzing a sequence that's in a reset condition, that is, one in which no events have yet occurred. At that time, an event counter, which monitors the progress of the sequence, is equal to 0. This indicates that there is no sequence currently in progress. When an event occurs, a 5-second event window timer starts, and the event counter is incremented to 1. If another event occurs before the timer expires, the timer is restarted and the event counter is incremented to 2. If events continue to occur with the proper timing, an alarm is flagged when the number of events equals the set event count. At any time in the sequence, if an event does not occur within the timer window, the event counter is reset to 0 and the sequence starts over. Let's analyze such a sequence in graphical terms. In this example, we'll assume that the event count parameter is set to 3. Note that the event window duration, that is, the length of the window timer, is set to a fixed value of 5 seconds. The sequence starts when the first event occurs, as indicated by the red vertical arrow. At this time, the 5-second event window timer starts, and the event counter is incremented to 1. In this case, a second event, again indicated by the red arrow, occurs within the event window. The event window timer is immediately restarted, and the event count is incremented to 2. The APU is now waiting for another event. Once again, an event occurs within the event timer window. The event counter is incremented to 3, and since we've set the event count parameter to this same value, this constitutes an alarm. However, if the third event occurs outside the timer window, as shown here, an alarm does not occur. Rather, when the second event timer window expired, the sequence that was in progress was terminated. At that time, the event counter was set to 0, thereby resetting the sequence. When the third event occurred, as shown here, this was simply the first event of a new sequence. The last two parameters aren't really alarm processing controls, but they are related to the alarm outputs. They are listed in the miscellaneous area of the parameter table. These two parameters are alarm relay time and tamper enable. The alarm relay time parameter controls the duration of the relay alarm output. It can be adjusted from 1 to 10 seconds, depending on the needs of your alarm monitoring system. The tamper enable parameter controls the tamper input function. This function accepts inputs from a normally closed tamper switch that's physically operated when the APU's NEMA enclosure is opened. When this occurs, the alarm relay signals the monitoring system to notify it that the APU is being tampered with. This concludes our discussion on the FD322's theory of operation.